Hello everyone, my name is Rizk, and I would like to present to you in 15 minutes a case study in face recognition. This case study is the final project for the Computer Science E89 Deep Learning course at Harvard University Extension School with Professor Zoran, Djordjević. Face tracking and identification has become a common concern to many organizations, as it has multiple use cases. It can be used in marketing to analyze customer behavior, or to identify a VIP customer when he gets into the shop. Of course, it can be used for security to detect intruders or by human resources. We are going to achieve that in 2 steps. First, we need to locate face in an image, and then we will have to identify the detected face. Let's talk a little bit about the data. We will be using the wider face dataset. The wider face dataset is a publicly available dataset. It contains more than 32,000 images and labels of 393,000 faces. It has a high degree of variability in scale, pose, and occlusion. In our case, we need this variability because we want our network not to be sensitive to occlusions like sunglasses or pose if someone is not totally facing the camera. We'll also be downloading the pre-trained model for the VGG face model developed by Oxford University. We'll talk about that later. From a software perspective, the project was entirely developed in Python, and we had to install additional packages that are TensorFlow, KERAS, OpenCV, Build, and scikit-learn. From a hardware perspective, I was using my personal laptop, which is an Asus GX 501. It has an Intel Core i7 processor and an NVIDIA GeForce GTX 1080 graphical processing unit. Here are the steps that we will be following to solve our problem. First, we have to set up the environment. Once we have that, we can process the original data set, and this will help us build a generator that will feed our model with batches of data. We'll then train our model to identify if an image is a face or a background. We'll repurpose this model to create a face heat map that will highlight regions where faces are detected, and we will crop the face. Once we have the cropped face, we need to identify the individual in that face. And for that, we repurpose the VGG face model that was developed by Oxford University. And we will try and match the embeddings created by this model with the ones stored in our test photo dataset from known individuals. Once we've done all that, we have successfully located and ID'd an individual. We'll apply everything to our webcam video stream. So we've already been through the environment. Let's discuss the processing of the original dataset. As you can see here on the bottom left, the original dataset is a collection of images and with the bounding boxes of faces. From our side, all we need are the faces and the non-faces to be able to train our model. So what we will do is that we will crop the faces and store them. Here you can see that this lady here is face number 27. And then we will randomly select pieces of the image that are not faces, that do not overlap with faces, and we'll crop them and store them in a background folder. Now that we have those data sets ready, we need to format them to be able to feed them to our convolutional neural network. And so we need to transform them into floating point tensors. Luckily, KERAS has utilities that take care of these steps. The class image data generator allows to quickly set up Python generators that can automatically turn image files on disk into batches of pre-processed pre-processed tensors. As you can see here on the right, this code is relatively small. Now that we have batches, we can start training our model. So we'll build a convolutional neural network model because it's adapted to image identification, but we have two constraints. We want to maximize accuracy, of course, but we also want the model to be relatively fast because our localization algorithm will use this model extensively. So we actually will iterate on multiple levels of depth. So we tried multiple models with, here we have an input shape of 64 by 64. We tried input shapes that are more detailed, 128 by 128. We tried deeper models, we tried shallower models, and we found out that this exact model with 3 convolutional layers and 2 max pooling layers will allow us to achieve a 95% accuracy whilst staying relatively fast. So this is how we pick this model, by supervising the time it takes to do predictions on a full batch versus the accuracy of the model. The model was, of course, trained with an RMS Prof optimizer and the binary cross entropy loss function because it's a binary output, face or no face. Now that we have this model, we can use it to create a heat map for the presence of a face in an image. So we'll take a random image and subdivide it in a grid of size 10, 10, and then take all possible squares in that grid and feed it to our model that will predict if the face is present or not. By summing those predictions, the regions where the face is located will, of course, have a face predicted on it multiple times because it belongs to multiple squares where the model will say there's a face. So this is how we create our heat map, and from our heat map we are able to crop the face. So now we finish step 1, which is locating the face in the image. Now this was not my initial approach. I was trying to reproduce a gradient heat map implementation, mimicking a study by the South Korean Chonam National University, but the results were very volatile. It did function, but the regions on the edges were selected as faces while they were not. And I wanted a model that was relatively robust. This is why I went for this approach. But as you can imagine, it is very extensive and it will not be scalable. We'll discuss this later. Now that we have a crop face, we need to identify the individual in it. We'll use for that VGG face that was developed by Oxford University to recognize the faces of celebrities, as it was trained on up to 1,000 images per identity. This model used the triplet loss function. The triplet loss function is adapted to this case because it tries to maximize the distance between possible outputs. In our case, in our 2,622 dimensional vector space, we want each and every individual to be as far as possible from the other to avoid false matches, because we want the distance to be as big as possible. So now that we have repurposed this model is capable of assigning for each face provided a 2,622 dimensional vector that is kind of unique for each face. And we'll use that to actually compare with the faces that we have stored in our test photos folder. You can see that this network is relatively deep, as it has 37 layers, and that's why we did not retrain it ourselves, but we downloaded the weights. Now that we have a way of encoding a face, we can compare the faces that we have in our database with the one we just cropped. We use the cosine similarity as a distance metric. and because it's particularly adapted to distance that are in the same dimensional space. There's other metrics like distances can become very large. In cosine similarity, you can assign a threshold, and if the distance is between a certain threshold, you know that they're very close. So now that we have this threshold, if two embeddings provided, one from the database and one from the cropped face, are below this threshold, we'll say that they belong to the same individual and that we have identified this face. Okay, now we have all the pieces of the puzzle and we're gonna put them together. So the first model is used to crop an identified face from the webcam. The second model will compare this photo with test photos, and if there's a match, we put a bounding box and we show everything with OpenCV from our webcam video capture. This is a small summary of the different steps we just discussed. In conclusion, we have successfully implemented a face tracking and identification model. And we have implemented it on our webcam live video stream. I'll show you that in a minute. This being said, efficiently locating an object in an image is not an easy task, even if we can recognize it. So I successfully developed what I would call a brute force approach, but it's slow and not scalable, and it can only detect one face at a time. As a next step, what I would like to do is to implement a state-of-the-art real-time object detection system that will replace my current approach. And I was thinking about implementing You Only Look Once, YOLO, or also trying again the GradCam heat map approach. One more development I'd like to consider is linking frames in time using recurrent neural networks. Because right now, our model only looks at each frame independently from the others. If it identifies a face, it doesn't say that there's a higher chance of identifying a face again at the same location later on. And we all know that in reality, objects don't suddenly appear and disappear, and there should be some kind of link between the presence of an object at a certain period of time and maybe the second that is just after it. So now let me show you a little bit. How it works. Here it goes. Here it goes. That's the result. The model is actually looking at me right now, and it has identified me. That's it. And thank you for listening. Goodbye.